Log on, tune in, find out. Another good idea from Cambridge.
Panel, but I think I would like to start by saying thanks to a number of people who've made the whole workshop possible. I'd like to thank David Wallace and the program committee for the entire program, as Rosemary is here. Thought I saw Hugo wander in. And there's several, I think those are the main ones who are here. And then the fellow organizers for this particular workshop, Angela Berry, Bruce Ankerman, and Derek, all were working on this. I'd like to thank the I&I staff because they did a great job, I think, of answering all kinds of questions about local information and cab rides and everything else. And I'd like to make a special thank you to Steve, who's been in the closet back there, tape recording everything, trying to make us beautiful. So I'd like to do that. Thank you. Okay, so we're going to start with remarks, and we're going to go with the order here, Russ, and then Henry, and then David. And then we'll open it up, and the panelists will come up here and sit. So, Russ? And you're on?
Okay, good.
Stoplights.
All right, so integrating multiple modes of experimentation is supposed to be the focus of this wrap-up. I have to admit, I put one slide in on that, and then I sort of wandered a little bit after that. So let me see if I can make this thing go forward. Certainly that way I can. So what I want to talk about first is multiple modes of experimentation, where we think about F1 and F2 maybe corresponding to higher fidelity models and less, maybe more economical, but models with less fidelity. Or maybe one of them is in fact experimentation with the real system, so maybe F is the outcome of a physical experiment. So what I would say is that one of the comments I have to make is about the way the experiment designs are done in this setting. At least from this workshop, seems to be that these designs are nested, that from the assumptions that have been made, typically the high resolution model is run at one point, at points at which the low resolution model has also been run. But it brings up an interesting thing for me. There's an article that's in April's IIE Transactions looking at not really a computer models issue exactly, but more of a metrology issue, where you might imagine the situation is that the x's really don't, even though you think they're the same, they're not. So the lower fidelity model may not just involve changes in the response, but may involve shifts also. And in higher dimensions, these shifts might be more complicated. So I think there might be an analogy to the work that's being done in trying to integrate low resolution, high resolution measurements from coordinate measuring machines. And so then the cases that you're trying to not just combine the information you have, but align the coordinate systems or align the x's. So that's one thing I'd say might be worth a look. And if that's one of the things you're trying to pay attention to, then it probably changes the experiment design strategy a little bit. Because just that nested design may not be sufficient. So there might be some sequential experimentation strategy for that. And maybe second idea related to this, not tied to that, is we talked about discrepancy, and I'm not sure whether there was a nice discussion of how discrepancy, if we could, ought to be tied to what's actually missing in the low resolution model, and can that drive the experiment design? Can that knowledge of aspects of the discrepancy from the physical difference, the differences in the aspects of the physical system that are modeled, drive the design? And the last thing was, I saw a number of talks where, well, there was an experiment design for the low resolution model with lots of points and a nesting within that. So the one this morning, right, was 1,000 points for the low resolution design and roughly 100 for the high resolution design. how do we get those numbers? What's the right number for the high resolution design? And I guess the last point, which I didn't put here, is I got the feeling after hearing these talks that maybe we need to talk to modelers about what they do with their old models. So you imagine a modeler has a model from 1960. Well, that ran on the computational resources then, and it had certain inaccuracies. So they have a better model today, right? What do they do with the old model? They throw it out. But everything I've been hearing here says you should tell them to bring it back out and run it a whole bunch of times, and then they'll get a better answer with their new model than just running the new model by itself. So that was, I wonder if anybody else feels that way. Okay, I'm doing something wrong with this guy, that's for sure.
There's an on-off switch. I think it's on the socket.
Oh, I see it. Yeah, it was off. Okay. All right, so now I'm gonna go back to these questions about DOE in general, and I would say we've heard a lot of uses of, oh, it works now, see? No? No? Still doesn't work. That reminds me of the chainsaw joke, but I'm not going to do that one right now. So there's certainly validation. You never heard that joke? Never mind.
We'll see if we have
when you buy me that beer tonight, I'll tell you that joke. So this is the list of things that I saw today, and certainly going through the last talk today, which talked about thorough exploration, and these really, in my mind at least, everything that's up there is a different use. Sun talked about real-time calibration, for example, in changing the way the model's predicting the future based on what is happening right now in reality. So I think more careful thought about the use of the model should affect what the design criteria are. So that means some kind of explicit definition of objectives that would change depending on which of those uses or which suite of uses we had in mind. All right, so now my last couple of comments before I get to experiment design and experimental design. So the last comments are just an idea. A lot of the pictures that I've seen showing the Gaussian process model fits, always have this droopiness going on. And we looked at some of those, Roshan had some nice ideas on how to fix that. But I just had another suggestion on how to fix it, maybe based on things that happen in nonlinear programming. And so maybe if we're trying to keep something more or less the same locally, what we should be trying to keep the same is the second derivative, not the function. And so maybe for the Gaussian process model, we should be looking at the second derivative coefficients, or at least some of them, and having that be the object exhibiting spatial correlation, and then propagating that through, I guess, by integration or somehow to what's going on in the actual function value. So it's going to be a little bit backwards from the talk we had about integrating a measured gradient into the problem, but it might get the Gaussian process models to stiffen up a little bit. So you might be able to do a little bit of prediction or extrapolation outside the range. So Brad Jones talked about the compromise between de-optimal designs that you might have for low-order models and space-filling designs, and that really when you have a highly noisy situation, you really are, it may be hopeless to try and capture more than first or second order effects that I guess there's different kinds of Taylor here for us industrial engineers, but I mean the Taylor of Taylor's theorem, that maybe that's all you can trust at that stage. So is there a way to do that sequentially? So you, as you learn more and more about the signal to noise, you make designs that go either more towards space filling or more toward a more traditional de-optimal design. And the last thing I didn't hear much about, and actually I'm disappointed Jack Klein is not here because I love to fight with him on this issue. So there's a lot of talk in stochastic simulation about having different variants at different points in the design space and requiring you to have different numbers of replications. And so my feeling is that that's true whether you're talking about a real system or you're talking about a simulated system. I don't think there's anything special about stochastic simulation, and statisticians solved that, in my opinion, in many cases a long time ago. with things like box-Cox transformations. And the nice thing about those transformations, in my experience, is the same transformation that stabilizes variance simplifies the response surface. In many cases, it simplifies the response surface. So I didn't hear much talk about formal ways of deciding how to either transform the output in that way, or of course there are also issues about transforming the inputs. How do I transform them to make more sense? And so I think, to me, that's still a part of experiment design, because I want to do my design based on these guys instead of based on those guys. All right, so last comment is about experiment designs and experimental design. So this is an apology to the UK folks here, and I know the tradition began here, but this is an American's perspective on experiment designs, which is what I like to call them, versus experimental designs. Now, I know on the first day there was a talk that involved designing a spoiler on a car, and I like cars, so I thought that'd be a good example. So what I have on the left-hand side of this is what I would consider experimental designs of cars. So each one's an experimental design for a car, and it might work and it might not. It's an experiment. This one I like a lot. I don't know if you can get a motorcycle license for that motor home, but it was certainly an experiment worth trying. And the other side is experimental, is the real experiments, and these are designs for experiments. So this one I know it's hard to see. Does anybody know what that one is? Yes.
It's in Wales. It's a Latin square with different types of trees in forest. Fish are laid out.
Fir trees, large trees, things like that, a Latin square. And some of you probably have been around to see this one, I guess. In, what is it, Keys?
Yeah.
Okay, so now let me try and give one more justification for experiment design versus experimental design. So you see the little boxes at the very bottom of this slide. So anybody know what this is? Let's start with this one over here. I know it's kind of hard to see. Let me give you a clue. These are ornaments. And this is a frame for the ornaments. If you Google ornament tree, that's what you'll get. You'll find lots of pictures like that. That's an ornament tree. So what's the thing on the other side? It's an ornamental tree. Okay,
Henry?
Sure.
Yeah.
Get it
Tell you
up.
what, if you work on that, I'll work on yours.
Clarified a lot for us.
How does this work? Strangers in the night.
Don't have any words that many syllables.
I have an extraordinarily loud voice anyway.
I think it's just to make it pick you up.
Okay, so this is a laser pointer to take the eyes out of anybody. I just thought of that. Anyway, so I'm going to say very little, and I'll be rather fast, but some of it's a bit philosophical, which is what happens to you when you get a bit longer in the tooth. So one thing I've been obsessed with for many years and never really written anything on it is the difference between passive and active experimentation. It goes back to John Stuart Mill. He called artificial experiments versus spontaneous experiments, and there's a huge literature on this tension between the two. And it's something we find both in, so that's this top, the columns are increasingly passive to active use of models, and also the big implications of course for experimental design. Even in optimization, which is really at this end, your choice of where to look in a function is a kind of experimental design. And also, so these are the big two divides, in my opinion, the passive active and the physical computer. In the physical experiments, for example, there's a whole area of social science, or observational studies. And I mean, you know, it's like a cat, when it's just half asleep, will just not see anything. As soon as a mouse, anything moving comes in, it jumps it. So even as humans, we have this distinction between the passive mode and the active mode. What is that? There's nothing, very, very little research of any of us doing on this distinction, and it's absolutely critical. So in computer experiments, obviously the same thing is lurking there. We have these Monte Carlo, Latin hypercubes, space filling, just put observations, take observations everywhere, just because we don't know what the model in will be very passive. Or you can have, in both areas, you can have model-based optimal design in computer experiments. Maximum entropy sampling, we've heard a little bit about. You have a model, you go in, you have your integrated mean squared error criteria or your entropy or anything, but so a model-based thing where for identifying the parameters kind of optimality criteria. And we might, and of course we use, they use factorial and optimal design in industry. Think jump, all right? So this is jump. And then we come strongly model-based. You only start to optimize when you really know your model, or maybe, of course, there's a huge hinterland here between this exploration, exploitation kind of issue, which lies right on this border. How long do you, are you greedy? Or are you a little bit more passive going for the model? Not this passive, but you want to go for the model here. And of course, a lot of special algorithms. We heard a lot of optimization. And I think, oh, now, he's doing stochastic optimization, and searching for some optimum here. And of course, not much fills this area. Not much fills online, physical experiments. Of course, Boxer's EVOP was that then. And then I would just come from the MBIS meeting in wonderful Portugal, and they have this simplex method. So they do, it's like EVOP, but they take, it's called the Nelder-Mead, the simplex methods, and make it physical. And they put a new point here and another one, a simplex here, and they have fixed step lengths. For God's sake, fixed step lengths? When the people in optimization would never have a fixed step length, so and so on. So there's a bit of a hole here, but apart from this is my way of thinking about the whole of experimental design and modeling. And we are somewhere here. And if we're going to have an argument, it's probably going to be on one of these boundaries. But I'm a bit too tired to argue anyway. Okay, so simulation. Now, I fortunately, I hope there's enough discrete event simulators in the audience that I can insult. So why, we've been doing this computer experiments now for 20 years. Why don't people build simulators which have the facility, built-in facility to emulate? The designs are sitting there in a catalog inside the simulator. Why are there two different communities? Simulators should carry the seeds of their own sensitivity design emulation. Of course, people in the know who do finite element modeling know that there's automatic differentiation. They can bolt on some scripts to get out the sensitivities, which are just Jacobians. And once you've got the Jacobians, you can do design, identification, optimization, etc. built in. Or adjoint methods, even in climate modeling. Where's Peter? Only sort of. Peter and his wonderful team in Peter Chan, wonderful team in Samtown, had to sort of build their own adjoint method. Why wasn't it in the simulator originally, right? So that poor statisticians either shouldn't spend hours, who are not, if it's me, are not very good programmers, building, okay, and also the ability for simulators. We've heard a lot, it's getting a lot better for simulators to work at different resolutions, for example, by taking subsets of designs and things like that. But we're streaks behind people who work in areas such as dynamical systems and fractals, where you might see the same system here at a lower level. It's a kind of copy, a kind of ghostly outline of the system up here, and it's all over chaos theory and physics. So we really should understand and build into our simulators they should be able to work automatically at different resolutions. I'm saying this is a message to people who and to people who pay for simulators. And no funds to build large simulators unless simple ones have been validated. All right, which brings me to my next. Is that controversial enough? Okay. No. So this is a quotation that I took for myself at 6 o'clock in the morning. Simulation with identification is like driving a car blind. So Even on the big traffic models, you've got to match something to reality, like the population size, when you can do nothing else. You know, when all else fails, get the averages, or it's and Sandra would say, get your thermodynamic limits right, all right? I mean, which is averages, all right? And please go and don't just run your simulator, please go and look at special new ways of measuring things, of which the most exciting from our point of view is sensor location. And that's a wonderful emerging topic. So sensor location is a type of design. We've had a wonderful talks, not this week, but earlier weeks on sensor location in the first week. And you want to measure something, you put a sensor here and you can measure. We're being censored at the time. I think I'm being censored anyway. Sensor, not censor.
Not by yourself.
Yes, no, never. Only my wife. Anyway, naive, formal elicitation expert judgment. Do it formally. I mean, there's books have been written on. Don't just say, oh well, I'll set the infection rate equal to 1.2. You know, go and talk to the epidemiologist. Use methods to elicit. And this is nice. This is another fake quotation. Every needless detail is an unidentified or unidentifiable parameter. Don't do it. Replace it by a stochastic, something stochastic. You know, nobody wants to know in disease modeling the friends of all the children in class 2B in the high school in Alabama. Not really. Well, you can replace them by sort of average, you know, because it's going to take 3 weeks to run, and meanwhile they'll all be wiped out by SARS. So, you know, I mean, it's just not on anymore. And also, and concentrate on the objectives. I mean, build a simulator because you want to cure diseases, not because you want to write sociological studies on sixth forms in Alabama and 10th grade in Alabama, right? I think of years of people collecting warranty data for cars, and terrible difficulty of using that for reliability studies because it's not intended for that purpose. Intend your simulator to be for a purpose. That way you might get money to pay for it. Okay, this is another 6 o'clock notation, quotation. We live in the spider's web of extremes. What's been missing from most of the talks this week, although I only attended 2 days, so I may be wrong, and earlier talks, is that big simulators are interested in risks. That's part of the objective, the last point on the previous slide is risk, right? So, there is a method, again I think I'm going to quote Peter twice, that of emulating using not Gaussian but extreme value distributions, which I don't know much about, but it's obviously something we should all know, right? And there's a large group now in insurance. You need to understand this, particularly in multivariate. You need to understand this multivariate dependence is big time stuff now, right? So, copulas, Bayes nets, things called vines are used now in finance. So you have a big portfolio. You look what's correlated with what. Look at the dynamics of the dependence as you go through time. That's the sort of thing we should be using in our simulators. And I think I'm right in saying that more and more I mean, of course you're going to do the mean and the variance and the correlation, but percentiles are going to be the thing you want to look at if you're looking for extremes. So things like Kriging percentile regression, right? So you're looking, the percentiles are the main things you want to look at, particularly for insurance. And interactions. This is interaction by, I mean, is smoking plus the wrong pills equals you die, right? So that's interactions are also very important. We had a very nice discussion this week about, I love interactions. And we had this, Angela's likes interactions and everybody likes interactions. Anyway, I just came from, this is the last talk I attended at the MBIS conference. This poor student, I think one of these people gave it, I think it was her. And I put my hand up and said, well, very nice talk. Why didn't Professor Herdel do this analysis in 1997 before the world financial crisis, right? So this talk had everything you could possibly imagine. It had multivariate, not Gaussian copula, but extreme value copulator. Sorry. I never lived that down, that's for sure. Copula. Is it? It'll go on my niece's Facebook. Copula. Copula and base nets, vines, and networks, percentiles. Okay, so they have that. It's dynamic, right? And they go back to the old data, and they showed with the right dependence, they would have picked up the world financial crisis. Of course, it's easy to be wise after an event. I have to say, with swarms of clever young people going into the finance industry, and with their martingale measures and asset pricing and capital asset pricing models and copulas and all that sort of stuff, why didn't they pick it up? Maybe we should get our money back. Anyway, there's a whole bunch of techniques in the financial sector, which this paper had a number, which we should be using combined with simulators, and particularly the objective end of our simulators in risk studies. And we're not doing it, really. Has anybody done copula? Careful when I say copula Krieging. Okay. And so on. Okay, that's it. Thank you.
Off here, Dave Aikman. All right, well done.
Well, no, terrible.
Brilliant. That's going to be impossible to follow. Here we are.
There you go.
There, it's awesome. There we go.
All right. So me, and then we have questions after this, right? So
Probing question.
all right, and thank goodness Henry was fast. Otherwise, it might have taken even longer. All right. So what have I got to say? God, probably not much. But all right. So I am from Los Alamos. So a number of applications there are big, multiple integrated physical systems. Take a nuclear reactor, for instance. There's nuclear reactions, there's material properties under radiation, under extreme conditions, sorts of things like that. That there is a sequence of experiments to tell you about how your model's doing over this whole entire range. And then quite often you end up using these simulations to say, well, what's going to happen if someone forgets to turn this valve on and accidentally moves this thing over there and moves that material over here? What's going to happen now? So you look at some event that really the model wasn't exactly built for, but you'd like to see what might happen in some very extreme sort of event. And so what do you have to try to understand this? You have your model. Usually it's a fairly complicated model, or it might be a series of models. One model might do the nuclear transport, another model might do materials under radiation, another model might just be pipes and valves and sorts of things like that. So either you have one big model or a couple of different models. But one of the questions that's out there that I think really is a function of design, it is a function of modeling and emulation is, well, how do we put this big apparatus of model, experiments, and simulations together for us to be able to say how well we trust our simulations for these extreme events, and then given that, how do we prioritize what are the things that we really need to look at in order to ensure reactor safety? So putting this whole physical system together, lots of different types of experiments, maybe different types of models, is a big kind of meta design question. And I think that one's going to be around for a while in a number of different places. And I think that's going to have a lot of rich research sitting around in it for a while. Tom had a few questions, which we were all ignoring, and I'll go ahead and ignore it too. But one of them was this idea about, well, can you really say anything? Now I'm not going to ignore it after all that. Well, one of them was this question of, well, can we say anything about calibration parameters if we have discrepancy? So certainly that's a hard thing to do because discrepancy is telling you your model's not reality. And so what you think might be the yield stress of steel in your model, well, if there's a discrepancy in it, maybe your model doesn't really have yield stress in for one of the parameters. It's something else, something like yield stress. So all I want to do is just give you an example of a project we're working on where I think I'm willing to trust the calibration even though there's going to be discrepancy. And this was this cosmology one that I had talked about earlier. And so reminder, here's a bunch of data from the Sloan Digital Sky Survey. The calibration of the model parameters is middle 90% is inside these green lines. Currently there's no discrepancy, and that's because the data are not that good. We know there's going to be some. And then we can go ahead and make our prediction here. But we've got this 5-dimensional posterior distribution of cosmological parameters. So what's going to happen in the next generation of large-scale surveys is that we're going to get more data out here. And now what's going to be really important is that the difference between dark matter, which the simulation runs, and light matter, which we see in these surveys, is going to become important. And so what we think is going to happen is that, or we even know this is going to happen, we just don't know the extent of it, is that the model's going to go up here, but the data are going to go down here a little bit. And that's because of this transformation between dark matter and what you observe. And so there's models to try to figure this out, but they're not going to be quite ready just yet. And what they do is they add on galaxies on these clusters of galaxies that you're simulating, and they turn it into something that you would observe. And so people know from looking at these models that the observation you're going to get is going to be a little bit below what the models are going to say that do these dark matter simulations. So here, we are going to be willing to start out anyway, use a crude model to help us kind of parameterize and characterize this discrepancy, but we think the discrepancy is basically going to be 0 for a while, and then for these larger Ks, we think the discrepancy is going to bend down in a nice continuous fashion. What we don't know is how much will it bend down exactly. And will it be straight? Will it be a slight curve? Something like that is going to be a little bit unknown. That's going to depend on how galaxies form and how these galaxy formation models work. All right, so we don't know that exactly, but we think we have a good idea of the form of this thing, and I also think that if we go ahead and put that discrepancy in, well, we're going to tell the model to match the data around here in this area, and we're going to tell it you don't quite have to match here, but I think there's still going to be information. So there's a case where we're going to end up with a posterior distribution that we think is relevant to cosmology as much as one's parameters might describe cosmology anyway. I think they're only relevant through a model anyway. But there's an example where I think it's probably going to work, and it's really nothing fancy is happening. We're just being very thoughtful and specific and tedious about what's our prior specification for this discrepancy. So there, I think it works okay. And I won't go in order either, but I will not say copula anymore. Note to self, I'm never saying that in a talk. So Derek talked a little bit about this. So this is also about discrepancy, which is probably something worthwhile, but I think it's a way that, well, how do we build discrepancies in a way that we might be able to trust the model results? And one way we do it is, just let the modelers put it in. In fact, you look at all their physics, and most of them are what we might call discrepancy models. They're just embedded in some sort of way. And so here was this example where we take bowling balls, basketballs, baseballs. No cricket balls in here. It's not a transatlantic talk, apparently. And you drop them off your tower here, and so you can send the grad students up to the first floor, second floor, whatever. And you can go ahead and get drop times for a given ball. And so it turns out if you do a bowling ball, make sure you have a first-year student should do that, take it up to the top tower, and drop that. Well, it's not going to be affected by air resistance, so no drag there, pretty much, for the sorts of things we're talking about. If you take a basketball or something lighter, a tennis ball, you're going to see air resistance. That's going to creep in. And so if you just did bowling balls, if that's all your university did, you wouldn't think about an air resistance model. You might, but when you start throwing in these other balls, air resistance is going to creep in. And what the modelers do is they put in a term that's a common term for drag. It's physically motivated, but it's not a first principles model by any stretch. It's not modeling turbulence and eddies going around the ball as it's flowing through the air. It's just a term that says, the force of resistance is proportional to the density of the air times the cross-section of the ball you're dropping. And they'll do wind tunnel experiments to try to get at some of these parameters, but that's about it. So this example just shows, here's drop times, these black dots for a basketball. Here it is for a bowling ball, and here it is. And maybe we want to predict a softball or something like that. Well, so we've got these two parameters sitting out here. One is the acceleration due to gravity. The other one is this coefficient in this air friction term. So I would just say, well, that's a discrepancy model. That's just embedded into the PDE or the ODE in this case. And so now, fitting the discrepancy is just a calibration problem again. It has a lot of physical motivation, so that if we actually calibrate this model on these three balls here, basketball, baseball, and bowling ball. Everyone knows what baseball is? Yeah, I'm sorry. I apologize for all of America for that. Oh, is this recorded? Oh, never mind. They won't turn to this anyway. I know what they're going to go to in the recording. Anyway, I can't help myself. I'm sorry. but here's the idea: is that all right? So here's a softball. Here, because of this model, we might trust its air resistance. These things are all spheres. They're semi-uniform in density. Not really. The basketball's inflated and things like that. But here's the softball. Here we have the baseball. So we have three balls that we have data from. We're predicting for a softball. Somehow we're making the case that we think we might trust this drop time for a softball that our model plus the experiments are predicting. All right, so here I would think, well, subject to what the guys that know about the aerodynamics of this problem would tell me, I might be willing to trust this calibration as well. So it's also a discrepancy model where we think we might trust it. How far might you trust this? Might you push this thing? Like Derek mentioned, if you go out to golf ball, well, do you trust that? How far out here would you go before you quit trusting your model? I think that's a tough question, but I think now we're back in a physical space. I think the concepts of experiment design, are relevant here. And so exploring these physics spaces to say where are things in extrapolation, where aren't they, I think is also relevant for design for us. All right. Henry already talked about this, but I thought I would go ahead and do it myself as well. So in the computer model world, there's two types of scenarios that we get into. One is in which our computer model is like a cyborg. It's part machine, but it's part human. It's got the human sort of conscious thinking for it. It's telling you, it's helping the computer, the machine, the robot deal with extrapolations. It has all the things that physical data are going to help your model with. So in lots of cases, we don't just train our model and then just let it run and make predictions. We continually train it each day. This happens a lot, say, in weather predictions, something like that. Every day, you'll feed in new information to this thing, and you'll continually train this thing, and you'll know when it can extrapolate, when it can't. That's sort of the cyborg situation. You have this human intelligence helping the thing out. So it's the human is taking the place of the data, right? So you've got data helping the thing out. You don't have to be quite as good at modeling there. You're allowed to put in more empiricism. And because you have repeated observation, you can test things out and ask, do I trust this model or not for this situation? So weather is a good example of this, but I think a lot of the examples we saw in stochastic modeling are in this sort of realm, that there's lots of data to update this thing. There's lots of thinking about maybe you don't need all this detail in the model. You can put in an empirical fix here and there and then just see if it does better on the data that you've got. So you've got a good path forward to saying, oh, I'm trusting my model for this because I have all of this past experience. The problem with lots of applications we have in the computer modeling world, say climate models, for instance, is that those things are basically robots, right? We'll try to calibrate, we'll try to estimate discrepancy, but in the end, we shove that thing in the model and then we just let it go, right? They're just going to go off on their own, make the predictions that they're going to make, and we have to decide are they any good or not at the end, or how much uncertainty do we attach to them. And I think that's a hard thing to do because there's no data kind of holding them in. There's no conscience in these things trying to make them more human. I know you guys are going to ask, right? Arnold Schwarzenegger, isn't that a cyborg? Well, he was a robot covered with skin, right? Yeah. All right, so when we have these often updated models or repeatedly testing against observation, I think we could do a lot more in empiricism. And I think also the design questions are probably a lot more interesting on that side, because now it's more of this adaptive, reactive sorts of designs that we can be less passive there and try to figure out what it is that we want to do with that. And just, you know, what do we do in the cyborg world, or when we have lots of data? I mean, this is the filtering. This is the data assimilation world. And so we can run the model. Here are these blue sets, you know, as a prior run, but then we see data, we constrain them, and can continually do something like this, that we're always constraining these things given new observations. So even if that model's not reality, it might give us very useful predictions. And of course, we have the past to say how well they're going to do. And so things like an ensemble Kalman filter is exactly what we'll use in a fair number of weather predictions and things like that. So they can deal with very high dimensional systems. We can get uncertainties. And the idea is if our model's better, then we probably reduce our uncertainties and we might be able to predict a little bit farther out. So we can see when our model's better or not. Like I said, in the other world where we've just got our computer model and that's going to do all the extrapolation for us, and all we can really do is just think about, is it going to be trustworthy or not there? I think that's a harder world to work in. But if we can put some structure on that problem, like is there a design space that the experiments live in that we think has some continuity and we think is relevant, that's going to help us out quite a bit. And it's also worth noting that sometimes this design space is in the model, like it is here, radius and density. Well, those two things are in the model. Things that aren't in the model, like the shape of the ball or the object, those might also be important things in the design space. And so it's probably worth trying to figure out, you know, how do we lay those things out, and how do we figure out, have we got that covered, or the right elements covered there? So I think I'm going to leave it there. And Henry also mentioned this rare high consequence events, which I think is also relevant to the computer modeling world. It's one way to extrapolate out to these very extreme events that we think we want to guard against, protect against. What's hard about them is that because they're rare, we rarely observe them, so there's no data. Also because we're searching for things that are extreme. We don't really know if they're physically things that could happen or not. And so even if our model can get there or cause some sort of, you know, wild events that we think we ought to be worried about, that's just the start. Then you have to figure out, well, could that really happen or not? And so we have a number of issues that show up in rare events that I think are important for design, important for decisions, sorts of things like that. And I think, you know, we do have techniques out there like extreme value theory, or this basic principle of, okay, you have a very rare event. Well, do we have data on less rare events that we can help to try to bootstrap out there? And I think that's what extreme value theory does. That also uses a lot of model to get out there, but the fact that we've got computational models can also help in that. And so maybe combining those two fields, I think, would be something of interest. All right. I'm done.
Thank you. So we're going to now move the panel up into the front, and we'll pass out cricket balls for you to throw at them. Questions now, comments from the audience, things that maybe you saw, things you want to dispute with them. We're wide open at this point. So who would like to have the first comment, question, or whatever? Yeah, I should.
Or toss.
Yes.
So Russ was talking about transformable variance reduction, or through Box-Cox transformations or other kinds of transformations, and I think that's often possible, but when the mean and the mean model and the variance model are not functionally related, then if you try to do one of these things, you end up with a horrible mess. And so, for instance, in the case of a Taguchi kind of situation where you have a mean model and then a variance model where the variance is a function of some factor, not a function of the mean, then if you try to do a Box-Cox transformation, you don't actually recover what's actually going on. So I think you have to be careful about that.
Good comment, I agree.
Could, I mean, on other sessions, weeks of this workshop, we've had some excellent sessions on design for variance components. So keeping the variance components in there, not eliminating them, but designing for them, is obviously and it's a very hard, it's not a completely solved problem. Several people in the room are working on it.
I mean, let me add that Matt Schonlau in his thesis looked at I think systematic ways of developing transformations of responses in order to fit stationary Gaussian processes better. So in other words, transformations to stationarity so that that type of model would have better predictability, at least in terms of interpolation. So there hasn't been much, but there's been a little bit. Yes.
So I'm just going to jump into the same similar topic. And Dave, in your ball drop example, the radius and the density of the ball appear in it appears in the denominator of that kind of discrepancy, right? So really, you could design on the product of those two things, right? I suspect. And so do you get to ever, like in the simulators you deal with, do you ever get to peek inside and say, if somebody says, well, these are the knobs you can dial, but instead you do some sort of transformed version of the input space. So you're going to look along. So here you could just design on the density radius array, if you will, or some contour like that. Do you do that?
So I think for smaller projects where you're actually talking to the guy that knows the model, that can happen at times. And for a lot of these bigger projects, no one person really knows this whole model, or if they do, you're never talking to this person. And so in lots of other cases, especially the bigger, more complicated models, almost never do you really get to do that. But what often happens is you'll find some effect that some perfect multiplicative interaction shows up somewhere where the main effects are zero, but the interaction effect is really strong. And you go find this out, and you go hunt it down, and then sure enough, it turns out that some term of the model is in fact a ratio of something. That we should have just designed for that. So often after the fact for the big models, but for smaller things, yeah, you can talk about models, and often you can come up with smarter ways to parameterize it. Often after the first 3 studies you try.
In some things like PK models, if you estimate, there'll be some groups or ratios or combinations of parameters which are identifiable in steady state, but not, but in some sense more parameters or groups of parameters identifiable when you also include the transient part of the model. So actually, yes, you can take a Jacobian and try and identify your sensitivities and bundles of parameters, linear combinations, ratios, or logs of ratios, or whatever, which are more identifiable. So yes, one should certainly do that if you can, I think.
Yes, Conti.
It's a similar observation, but in complex codes, you often find that across the combination of parameters, you'll have some parameters that are switches, and others that are continuous. And typically, the switch will activate a module, right? And if the module is not activated, then the continuous parameter will not show up at all. And the key thing about structures like that is, if you are emulating this complex code, you need to know that or discover it. And when you do know it, of course, it changes the way that you structure your emulator, because you want the switch being off to neutralize the continuous parameter to hold with probability 1. So that's easy to do in the regression terms, but of course you have to work quite hard if you're just having a no-brainer residual term to actually put that in. And I don't think we've really explored the options for doing that in a coherent way enough yet.
Well said.
Comment on that one a little bit. There are cases where that's known, though, right? So, for example, there are we worked with some models that were looking at desk illumination and doing it via ray tracing. And so, when the model is transparent enough, you can say, for example, I need to know whether or not that ray hit the reflector of the lamp or went directly to the desk surface. As you're changing the dimension, the angle, let's say, of the reflector on the lamp, at some point that same ray is now going to be reflected off the structure. And so I agree with you. And in that case, it's interesting that you can think about constructing sort of state selecting approximations where you have the state information of these discrete variables, and depending on the state, you're actually using a different fitted model. Now you can actually have very clean, non-differentiable points in the response surface. I'll tell you though, the difficulty with those kinds of models is the usual measure of fit can be quite bad, because if you have captured a sudden jump in the function, but it's off on the x-axis by a little bit, and you compare that with something that's done a smooth interpolation, you can get a lot of the errors you can measure are worse.
Question. Alessandra, you had written me. Did you want to describe your drug area, which is sort of something which hasn't come up at this point?
Okay.
Yes.
This is something different I want to talk about. I have done a review of simulation in clinical trials. Whether we like it or not, clinical trials get simulated, and I think this is some concern for all of us. I have discovered this about 50 recent papers, not just in drug development, as we were talking about that, but in many, many different fields. And so there are guidelines going back to 1999 with a section on design. So I thought maybe as a statistical community interested in design of experiments, we should perhaps look at that. And first of all, one thing to keep in mind is that a simulated trial has got 3 models running at the same time. One is an input-output model, which would be PDPK in some cases, or other models. And then there is the covariate distribution model, and there is the execution model. So I wonder what the design implications are of having these 3 models together. Then they talk about protocols for simulated experiments, meaning the design of the whole simulation, not just the design of the single trials. So this is something that it seems to me would be interesting to look at. Then, talking about simulated trials, a lot of design issues that we are concerned with in real trials become, well, maybe they're not interesting anymore, like all the ethical problems. You know, we're trying to design adaptive trials in order to, but, you know, if you're simulating, maybe that's irrelevant, and you should look at something else. And then the really important issue is validation. From my experience, and from what I've been looking at in those papers, validation is based almost always on metrics, distances between observed and simulated points, descriptive statistics, no real statistics at all. That's my...
Thank you. Do any of the panelists have any comments, experience, or whatever?
Well, I mean, in a way, supporting what I said about, obviously not in this room so much, but in our fields where validation is not really carried out properly, and you're telling us that these clinical trials is one such area, perhaps even more worrying, because you're dealing with life and death of patients and survival and that sort of thing. So, and also your point about ethics. I mean, we've talked about this quite a lot. I mean, it may be that patients who are early on the trial are at higher risk than people later on the trial. So there's a huge number of ethical issues using simulation in this area. Actually, there's one area though where it's been really quite successful. That's in surgery, so which I have been a bit involved with. And there, of course, if you don't validate your simulator, you cut into the wrong organ when you're doing the surgery. So there, it's done extremely cleverly, the way that the 3D CAD sort of image is mapped into the actual organs in real time, while the surgeon is actually cutting the right organ out. So there are areas where the validation necessarily has to be extremely good because of the very high risk. Though in other areas, the very high risk does not seem to be pushing people towards better validation. Maybe the surgical knife has something rather scary about it.
Anybody in the audience want to add to this, or have any experience with this? Trials?
I'll just say, so not directly related to the clinical trials, but there are a number of procedures that have been developed in simulation that really are looking at this adaptive type sampling. So I think there's an interplay there. It's a little easier in some circumstances in the simulation world because you don't have to wait for that time issue. You've got something that in a clinical trial would take a long time for you to observe whether it's a success or failure. That's problematic. But certainly some of the selection-based procedures have developed quite a bit in the last 10, 15 years in the discrete event simulation community. And it may be that not all of those have carried back over to statisticians that have been working more in clinical trials, but there's some possibilities there that might be of use.
A very quick one. We've heard a lot about, in a Bayesian context, how the utility, the big utility, will affect your design. Expectation, the pre-posterior expectation of utility is what you want to improve because of your experimentation, but not much about these utility functions. They're going to be very complicated in medicine because we've got toxicity and efficacy and all these things Sandra was hinting at. And so how the mapping from the utility to the design is something which hasn't really been mentioned. I mean, you know, we need to understand how that happens, how a utility function affects the design, and sort of concertina the mathematics in between.
And I'll chime in also that design puts a different sort of stress on the simulator compared to, say, just making a prediction. And there may be features about it that are important to capture for design that maybe you don't need to capture for prediction, and vice versa. So that it seems like that validation idea is a pretty rich field. That in the engineering world, it's very focused on make the case that your model is representing reality to within a certain degree of accuracy, and then over what sort of domain are you talking about. So it's very well specified. People have gone down this road, even though I think there's lots of open questions there in the engineering world. It sounds like much more in these stochastic models, or even these clinical trial sorts of designs, that it seems like a fairly open field with some very rich, interesting questions in there. And I do know in practice people tend to go much easier on their model if it's just for making your design. Oh, as long as it gets trends right, it should give a reasonable design or something like that. And I don't know, where the dangers really are in making, broad statements like that and not really checking them out.
Okay. Other areas on the stochastic side, on the deterministic side, that people want to chime in their own experience or say things that they've seen here that they're going to particularly take away?
I have a question, but it has nothing to do with what I'm going to take away. My question is actually a pretty old question, but both of you guys, or two of the three of you up there, mentioned the role of subjective judgment or expert elicitation of quantities. And so in particular, Dave, since you work at a government institution, right, with policy making, and you have to worry about bombs blowing up and whatnot, when in your case where you get to the end point and there's really no data, you have to use expert judgment, right? How easy is it to convince them? Oh, and are they convincible, right? And then, then how do I? and it also applies to like the financial community too, in terms of if we're going to be able to really think smart, right, and then possibly develop some financial regulations. What do we have to do in order to be able to let these expert judgments come into policy?
I'll chime in real fast. I think my experience with big decisions attaching these things, and then, since we're being recorded, Los Alamos will rarely chime in about policy. They'll support things and say, well, here's the information we have, or here's our opinion about this decision. And then luckily we don't have to make a lot of them. But I think most decisions, the scientific part where I thought, all right, here's like you can't prove the case any better than this, regression line, trend, no error or anything. Oh, that was, 10% of what went into the decision. And I think lots of other things do go into that. And probably the closer we can, just like we do better in these sorts of model simulation-based applications, the better we're in cahoots with the modelers, the better we do, the more ground we cover, and the better buy-in we have. I think it's probably the same for the decisions, that if we want to affect those decisions well or be a big player in those, then we have to encompass these people from the get-go, which is no easy feat.
So my experience has been it's hard.
Important in this, in finance and in medicine and other areas, safety, I'm sure, the role of the regulator is very important. So, I'm not an expert, but certainly for Basel 1, 2 and 3, the financial regulations, modeling is fine, and what they really want is for the decision to be informed by the model. So in that sense, and obviously in health it's very important that modeling is done, but I'm not sure the regulators have taken on board the issue of elicitation of expert judgment in a formal sense. And maybe they don't want to do that. They just want to make sure that the expert makes a decision, knowing that they have correct capital allocation and all the right pieces are in place. But it's a very interesting question. I mean, it would be nice that somebody could ask the regulators what they thought about expert elicitation.
Well, I guess the one thing that worries me about eliciting expert opinion for an input for a model is it's like a sample size of one. So I'd say my perspective would be that if you have multiple experts you can consult, then at least that would give you some feel of range that you might be able to use in a sensitivity analysis then. And with that sensitivity analysis, if the results were not changing decisions, then you might have more comfort with the expert opinion you got.
And oftentimes, though, there's just no data to be able to support these expert judgments. Or in the case of simulated or deterministic computer models, the expert is contradicting the simulator, right? So, for example, in Dave's problem, the data were going down, but the expert's saying, no, it's going to go up, like the exact opposite. So it's really in your face that the experts are contradicting the supposed data that's available to you. And so, yeah, just wanted to.
Does utility, in view of all this, have any strong relationship? Should it have a strong say in guiding how an analysis is done? I mean, if in fact the utility that the statistician or analyst uses is in fact not that of the decision maker in terms of data and so on, does it make a difference?
So I'll give my opinion on that. I'm very uncomfortable about utilities. I think they're generally not computable, or when they're computed, they're wrong. So my preference is to give, and I saw a lot of my preference in the slides, my preference is to give results that show the range of uncertainty, preferably not just as a range, but as an estimated distribution. And then internally, the decision makers have some kind of utility function, but I'm not sure you'll ever get it out of them.
Maybe I can disagree a little bit with that. I mean, I think we live in an era in which, like an old operational research where everything, people want everything optimized. So in that sense, it's really very difficult to escape from a utility. If only we just use it as the objective function in an optimization. Of course, it should be like it should be a robust optimization thing with a like robust design with a mean and a variance and all that sort of stuff. But which happens in finance, of course. But I don't think we can escape utilities. If we wouldn't have any economics departments at all if we really escaped from utilities.
Well-made case for utilities.
I think what we need then are articles about soliciting utilities from decision makers somehow. Because if that's sort of a critical thing. Yeah, so.
Actually, I think directly to your point, this notion of what's the utility function you're using and what is this decision maker's utility function. And are they really the same thing? I think that's a huge issue. And John Burge had a talk at a recent Informs meeting where he said he was looking at a lot of studies in operations research where they put a lot of effort in and then the results were ignored. And his sense was that what he was doing was he was sort of optimizing for the community that he thought he was sort of working for, like with the airspace, the decision to close the European airspace after the eruption of the volcano in Iceland. So he was thinking about these folks being the community, the entire European community. He was working with the person who had to make the decision whether to close the airspace or not. And if you're that person sitting in that hot seat, you're going to be pretty risk averse, right? Because if you say go for it and the plane goes down, you've lost your job. But if you say close it down and then you're safe, then maybe you're going to sort of err extremely towards that direction. So I think there's a huge issue behind what's your utility function as an analyst and what's the utility function of the person you're working with.
I mean, I agree entirely with that. Something really worries me, and that's NICE. We heard NICE, National Institute of Clinical Excellence in the UK. Well, and who was it? Jeremy has a link with NICE. He's not.
But he is an expert.
Now I can. But they do have utility models, willingness to pay models, quality of life models. They are literally trading health with lives in these organizations. So at the very least, we need to open up the debates about the utilities that the government uses versus the other people use. So I absolutely agree with you. Let's open that. I mean, I might spend some serious time on this myself, but to try and find out where these, the ethics people call them hard choices, is the technical word in ethics. Where are the hard choices made in public life, and if our work is going into that place where the hard choices is made, we need to know a lot about what's going to take place in that room.
Let me just ask, in the electrical industry, the French group, to what extent do statisticians and analysts, their analyses, to what extent are they respected by decision makers at upper levels? I mean, that's another sort of area that's, it's very context specific and so on.
So your question is about the relations of the statistician.
Yeah, utilities that decision makers use. To what extent do they align with utilities that you as an analyst or statistician might use? And to what extent do findings that you might use as part of a recommendation, to what extent are they respected by the decision makers in your industry? Consultation.
Yes, no, but
consensus.
In fact, it's more complex because we have some safety authorities. So there's a relation with some.
So there's external regulations that
yes.
that constrain decisions, I think is what you're saying, right?
Yes, that's what I want to say. And so we have to prove some safety criterion. We have to prove the level of risk that we have with our system.
Right. It is low or something. So we
have not a lot of relation with the decision maker.
Yeah. So extreme events are critical in this industry, yes. Other comments? Yes, Jonty.
So I'd just like to pick up on the same theme because we see it a lot in the area of risk and uncertainty and natural hazards. It's an area that I've been working in for about 3 years now. And it's already very hard to get the natural hazard experts to quantify their uncertainties about the hazard itself, that is about when the earthquake will happen, how large will it be, and so on. But that's nothing compared to the gulf that exists between the hazard and the risk. So the hazard is basically all the physical stuff that's going on, what happens to the environment, in the immediate aftermath of an event. But the risk is the loss function, it's the utility that translates the footprint of the hazard impact into a loss. And that is the huge gap. And it's part of the reason is because, of course, there are many different loss operators for many different risk managers. It really matters whether you're an insurance company or a municipality, because in one case you're going to measure in dollars, and in the other case you're going to measure in sols, for example. So what's been happening in that field is that people have acknowledged, I think, that very little progress will be made on the difficult issue of translating hazard into risk. So people have almost acknowledged that the utility function is intractable and something that we could argue about till the cows come home, but nothing will ever get resolved. And what's happened in that field is that the products have adapted to reflect that, so that there are insurance policies that you can buy now that are indexed not by the loss, right, but by the event itself, called parametric insurance. So you insure against an earthquake. You don't insure against the number of houses that fall down or the amount of structural damage that's done. You insure directly on the scale of the earthquake itself. You say, okay, I get a payout if there's a magnitude 5.5 earthquake, within 70 miles of X. And that is a direct reflection of the fact that people can adapt in these markets to these difficulties in elicitation. And there are creative solutions there, and they're not always what you expect.
Interesting. Anybody from the simulation community want to add anything? Risk analysis is one of the topics that is nominally covered in our discussion in the days 2 and 3. Any comments about risk, extreme events?
Just a very quick one. I take John's point completely, that we're in a Norwegian project I'm involved with. Climate models need to be downscaled to a local level if the insurance companies are going to benefit from them, if indeed the climate models are true. So, there is a path, although a bit difficult, as Jonty says, to go from top-level computer modeling, downsizing, to the precipitation which hit the actual house, which was insured, and they got the rain damage. So there is a kind of responsibility, particularly if you're working in insurance, to really focus some of these large-scale simulators down to the local level. So I'm contradicting what I said on my slide about collecting data at the local level. And my view about this is that we need models we need physical models at the local level, on structural models for houses and runoff from hillsides and stuff, interacting with the climate models to have a whole system. So that systemic approach to risk, and somebody said it's not just the simulator, it's the bit outside, it's the whole system in which the simulator lives is the important thing, and it's particularly important, and that's what the insurance people tell us. They want all of that.
Okay. Anybody have any other points they want to raise? This is your last chance. Barry? Yes.
So I actually want to come back to something that you, Tom, asked me this morning that I don't think I gave a very good answer to, and so we'll see if the panelists have some thoughts about that. I think what you said to me, and you can correct me if it's wrong, is it seems like you guys in the stochastic community are very worried about characterizing the uncertainty in the environment, in nature, and making sure you understand how that propagates through and affects your decisions. But you don't seem to be interested in discrepancy at all. Right? I'm making it more extreme than what you said. But that discrepancy seems to not be the issue. And I gave you, I think I was short of caffeine at that point, and said something like, well, we're dealing with big macro level structures and we can actually see what happens. But I think the actual more correct answer to why we don't, and I agree with that, is that in most of the problems, many of the problems that we're dealing with, we're trying to put things in rank order because we're optimizing. And there's a belief, an implicit belief, that the discrepancy is sort of affecting everything the same way and it won't cause me to misorder the alternatives. When we're in a context like sometimes my colleague Jeremy Stamm in financial engineering, where we're very interested in the actual number, then discrepancy or how far we're missing does actually matter more. And I'm curious in the computer experiments
folks if there is sort of the same general feeling that discrepancy is not so important when you're optimizing, when you're trying to just put things in what's best versus when you actually need that prediction to be right. And I think the first thing that will happen is Russell's going to disagree with me about my original.
I want to go last.
Okay.
All right. All right, then clearly the least important answer to go first. And so I think that's right. I think typically the first order discrepancy everyone has in their mind is just a constant shift. And so that's something that all scenarios will have. And if it's the same thing, well then ordering, relative trade-offs and things like that are going to be unaffected. So certain features of your model or your simulation will be unaffected by that. So I think that's a reasonable description, and I think people often will say it in our world, saying, "Oh yeah, I don't trust my model to get it right, but I trust it to get the changes right. So that if we make this thing slightly more massive, here's how it's going to change the outcome." And so I think that's a popular approach for thinking about that. I don't know how great it is in other situations, but it's certainly popular.
I don't have much to say, but except that bias is what kills models, and so if you can find a systematic bias, which is a systematic discrepancy from reality, and you can correct it easily, whether you do it in a Bayesian method or not. There's a fantastic method which I only just learnt about called the Doxum shift. You've got a CDF, which is always misestimating my CDF year after year. It's on precipitation. So you just take your CDF, put in a Doxum shift, correct it, and you're done. So
now it was Tom's that was wrong.
He's a climate modeler and I'm a statistician. I have the real rainfall, you have the predicted.
I have the data.
So ways of correcting models, however you do it, when you've got some suspicion of a bias, just add the bias or subtract the bias off and get it right. That's fine.
So you probably know what I'm going to say, and that is an issue that has not been brought up, at least in the part of the conference I was at. Is I think maybe I'll push the point to the extreme that you optimizers out there are like flatlanders. The world is flat people. So I think in many cases what the designers are really looking for is give me a design that does this. So that's an inverse problem. It's not an optimization problem. For the inverse problem, I think this bias issue is really important. So if you're looking for a design that does a particular thing, you're not going to be able to do the hand waving about the shift leading you to the same optimum point. And I don't want to say that that no problems are optimization. I certainly agree that there are a lot of optimization problems, but there are a lot of interesting problems that are inverse problems. We didn't talk at all about, we talked about calibration, but that's sort of getting the theta right. So if somebody gives you a y and you want the x right, or you want to find out if there's an x, that's a different kind of problem with a different kind of experiment design. So Max Morris, who couldn't make it here, and I are looking at that issue a little bit.
Russ, you're very nice. Was that the expected answer?
Yes, absolutely.
Actually,
yes,
just to add to that thought then, certainly I agree that we may not care about what's the absolute optimal point, but we might want something that's pretty good, right? And so that suggests that rather than seeking a particular goal, we're seeking something that's at this level or above, which gives me a little bit of confidence that maybe I can design an optimization algorithm that can find such a point, and so we'll make everybody happy. But I'm not sure it's actually possible to please both you and Barrow.
So now we come back to utility functions again. So if I give a designer a screen, and let's just suppose they have two things they're trying to optimize or make look good, and they can move the little mouse on the screen to different performance values on those things, and immediately see the design and the production cost as they move it around because they have a meta model or a surrogate model that analyzes that immediately. That's different from getting them to look at a Pareto surface or really define what those objectives need to be.
True.
Okay, Brett?
I just think it's really hard to believe that a zeroth order correction is going to be enough. And, making a shift certainly is popular because it's easy, but it doesn't seem very realistic. You know, a function is only always bigger than another function if there's only, you know, a zeroth order difference between the two functions, and that, you know, we don't think like that, do we?
Yeah, certainly from the perspective I was giving, I was saying even the zeroth order problems are problematic for an inverse. I mean, I agree with you that there are higher order problems than that, but maybe for optimization you can ignore that one and just focus on the more significant problem.
Of course, if we acknowledge this problem, then we're going to be obliged to deal with it, though. That's the real issue.
Okay, let me ask, are the Barry, Angela, any other organizers, do you want to make any final comments as we close here? Anybody? We do want to thank you for coming, Angela.
Yes, well, basically, thank you very much, everybody, for coming. It's been, for me, it's been a great time. I hope it has been for you as well. There seems to have been a lot of interaction. The staff have been talking about how everybody's been smiling and chatting together. So thank you very much, and I hope that people will continue to talk, not just go away back into our little boxes, but continue to talk to each other.
Certainly from the stochastic guys, we appreciated being included, learned a lot. Thank you.
Okay, so if you haven't seen the checkout logistics there, please look. If you're like me, you walk in and you're sort of blind to things that aren't moving. So but thank you very much.